All right, welcome back. In the last video, we introduced the second fundamental theorem of calculus. We looked at one example, compared it to how we solved using a limit of a Riemann sum, and found, hey, it's a lot quicker. So let me just jot it down, and then we will do a couple examples. The fundamental theorem of calculus, part 2, says the definite integral from a to b of f of x dx is equal to capital F of b minus capital F of a. So you have to find the antiderivative, and then simply calculate the antiderivative evaluated at b, evaluated at a, and then find the difference. So let's see here. With part A, we say, all right, what's the antiderivative of 6x squared minus 4x? So let's see here. The antiderivative of 6x squared, okay, 6 is a constant multiple. The antiderivative of x squared is going to be x cubed over 3, so 6 times x cubed over 3, minus 4 times the antiderivative of x. Well, it's x to the first power, so we have x squared over 2 is the antiderivative, and then we evaluate, eventually, at negative 1 to 3. So this is important that we use that notation, because if we didn't use that notation, well, then that would be saying that definite integral is equal to that antiderivative, which is not what we're trying to say. We're saying that we're about to use that antiderivative to evaluate, to apply, we're about to apply the second fundamental theorem of calculus. Now, something I did not mention in the last video, and I will mention now, is that I didn't use a plus c. Okay? Now, why don't I have to use a plus c? Because when you, in general, like when you're just trying to find an antiderivative, you have to use a plus c. Because that plus c means that there is an infinite number of antiderivatives. But here's the reason you don't have to. Actually, I'll show you two reasons. First off, capital F can be any antiderivative. It doesn't have to be any specific one. So if capital F is a antiderivative, any one will work. You can use it. Any antiderivative you want, you can use it. That is, you could say c equals 1, c equals 2, c equals 10, c equals 1,000,000, or c equals 0. 0 is certainly a possible value of c. So basically, we're letting 0 be the constant here. Okay? So that's why you don't need a plus c when you're applying the second fundamental theorem of calculus. However, what if you did? What if you put a plus c there? Well, let's show what happens. Plus c, and we're going to evaluate at negative 1 to 3. Okay? Well, let's just see what would go on. So I'm going to put some parentheses here like so. 6 over 3, that gives us what? 2x cubed minus 4 over 2 is 2, so 2x squared plus c, and we're going to evaluate negative 1 and 3. Okay, now the next part is simply to find capital F of b, and here's how we would do it. Just use parentheses. We're just doing arithmetic from here on out. So we're going to plug in a 3. Actually, yeah, I'll use parentheses. 2 times 3 cubed minus 2 times 3 squared plus c. So this is capital F of b minus capital F of a. So 2 times negative 1 cubed. Why did I write so small? 2 times negative 1 cubed minus 2 times negative 1 squared plus c. This is capital F of a. So we have capital F of b minus capital F of a, and now it's just a matter of doing a little bit of arithmetic. Let's see, but be careful, of course. Let's see, 2 times 3 cubed, that's 2 times 27. 2 times 27 is 54. Minus, okay, 2 times 3 squared. 3 squared is 9, so times 2, that's 18. Plus c. Minus, now, I didn't mention this, but it's very important to use parentheses around the calculations for capital F of A and capital F of B if each of those has more than one term. If capital F has one term, parentheses don't really matter. But if you have multiple terms, like here, capital F has 3 terms, I guess 2 non-trivial terms, but 3 if you include the plus C. It's super important that you use parentheses, because if you do not use parentheses right here, when you subtract, you'll get your signs all mixed up and you will end up with the wrong answer. I see that's probably the most common mistake when applying the fundamental theorem part 2, is that parentheses are not used, and then that messes up the rest of the calculation. So minus, we have 2 times negative 1 cubed, that's negative 2. Negative 2 times negative 1 squared, that's negative 2 times positive 1, so that's minus 2 plus C. Okay, let's see. What's 54 minus 18? 54 minus 18, well, that would be 54 minus 20, but then add back 2. So what, 26 plus C. And then we have minus negative 2 minus 2 is negative 4 plus C. And so we get 26 plus C, and if we distribute, we get plus 4 minus C. And so now you see the reason that it does not matter if we include the plus C or if we let C equal 0 and don't worry about it, because we have plus C minus C. The C's will always add to 0, as long as you do your arithmetic, of course, correctly. So 30. Again, way simpler. That would be a really tough Riemann sum, I guarantee you, because that's 2 terms. There's 1 quadratic. There's 2 coefficients. That would be a very tough Riemann sum, but we can knock it out, with just a few lines. Okay, so there you have it. Fundamental theorem makes your life easier, at least to start with. It'll get harder once the expressions get harder, once the integrands get harder. All right, example B. We have the definite integral from 0 to pi of sine theta d theta. Okay, so the fundamental theorem, just like we have up here, says first find the antiderivative. So equals, what's the antiderivative of sine? Now, of course, the rest of these calculations are predicated on me finding the correct antiderivative, or a correct antiderivative. And a antiderivative of sine would be what? Negative cosine theta. Negative cosine theta, and we'll just use plus C and not plus C equals 0 and not worry about it. And again, it's very important that we use that notation, because if we did not, then that's not a true equal sign, because that would be a antiderivative, which is not even the solution if we had those taken away. Because if those were taken away, it would be an indefinite integral, and this would be our answer. Okay, but we need to be intentional. Again, it's always very important to be intentional with our mathematical notation, and we use this 0 and pi to say we're about to evaluate at the second fundamental theorem of calculus. This is going to be what? Negative cosine of pi. Now there's a negative sign built into the fundamental theorem, so it's minus the antiderivative evaluated at 0, so that's negative cosine of 0. So it's very important that we notice there's a double negative there, because it's minus the antiderivative, which itself is negative. So we have what? Negative, what's cosine of pi? Well, that's negative 1. We have another double negative. Minus what's cosine of 0? It's 1. So we have double negative 1, double negative 1. That's 1 plus 1 equals 2. So that's interesting. Here, let's look at the graph of that one. Let's get Desmos going. Let's see. Sine x. Okay. So there's sine x. We're all familiar with sine. But we went from 0 to pi. So 0 less than equal to x less than equal to pi. And there we go. So basically, we found like one, one hump of the sine curve. And what did we figure out? That since obviously that function is non-negative, sine is non-negative from 0 to pi. So we found area, not just net area. We found area. We found the area of that little hump was 2. So, I mean, to me, it's really counterintuitive that trig, you get this like trig function, and the area of this region between the x-axis, 0, pi, and sine, that you get a nice number like 2. I would have, if you had asked me without having any knowledge of this, if that would have a nice number for area, I would have said no way. It's going to have like pi in it or something like that. It's going to have like square root of 2 somewhere, or pi, or radical 3. But it's 2. By the way, while we're here, let's look at the first one. We had what? 6x squared minus 4x. Now that's the parabola in general. We were only concerned our interval of interest was from -1 to 3. Okay. Oh, whoa, that goes really high. So there is our interval of interest. Now remember, we're taking the here. Let's doctor this a little bit. Let's make the y-axis from -5 to what was it? Probably like 50 or something. But let's make the step by like 10. There we go. That's a little better. Okay. But notice it's not non-negative. So we would need to be clear that the interpretation of example A is net area, because there's this little region down here that goes below the x-axis. Here, we could do this also. In fact, this is going to take me a couple times. Let's do this. Okay. Let's make them all blue, I guess. And let's go to the 0 as our first x-intercept. Here, I'm just going to shade it for us, just to show you the region we're talking about. This is going to be y is greater than or equal to 0. Oh, you know what? I do that over here. Y is greater than or equal to. Nope. Less than equal to. And yeah, here we go. Y is greater than or equal to 0. Okay, so there's like that first region. And then we need to say, okay, over here, we're going to say y is greater than or equal to 0. We're going to go from 0. Oh, what's that in x-intercept? 0.571. That's the approximation, at least. And we're also going to say, oh no, less than equal to, oh no, greater than equal to. That was right. We're going to say less than 0. Y is less than equal to 0. Okay. Oh yeah, there we go. So we have part of the region is below the x-axis. So that's going to be counted as a negative, and that'll be counted as positive. Here, I'll just make that red to show, hey, it's counted in a negative way. And then this other region over here, from this x-intercept, so from 0.571 to 3, we're going to say less than equal to, and then we're going to say y is greater than equal to 0. And there we have it. So there's 2 regions that are non-negative. So those are counted in a positive fashion. And there's that little bitty red region that goes below the x-axis. So that little area is going to be counted in a positive fashion. So basically, automatically, the fundamental theorem takes care of this for us. The fundamental theorem says, hey, there's 3 regions here. And it's going to correctly take care of finding that there 2 of the 3 are non-negative. Those will count in a positive fashion. And then this one in between, from 0 to about 1/2 is negative. The function's negative. And so that region will count in a negative manner to give us net area. So the net area of this region, little blue plus big blue minus little red, equals 30. And it's, to me, it's amazing that it just blows my mind that that's what the fundamental theorem does for you. It's really cool. Here's another one that's going to blow your mind. At least it blows my mind. Okay, so we have 1/6, the definite integral from 1 to 6 of 6/t. Sorry, 1 to e of 6/t. So it's a rational function. Okay, so let's think about this. This equals the antiderivative. Now, we have a property that says what? We have a property that says you can factor out a constant out of a definite integral. So I can say, 6 gets factored out, and I have 1/t dt. Now, do you recognize the antiderivative of 1/t? Remember, 1 over a variable to the first power is always going to be a natural log. So this gives us 6 times natural log, don't forget your absolute value, natural log absolute value of t, and we're going from 1 to e. Okay? And now we apply the fundamental theorem. By the way, if you ever factor out a constant, I like to do this. This isn't mandatory. If there's a constant, though, factor it out of your capital F of B minus capital F of A calculation. That is, 6, open some parentheses, and then do natural log of B minus natural log, oh, I need absolute value. Actually, I would have been lucky there, because turns out what doesn't matter. In general, it super matters that your antiderivative of 1/t is natural log absolute value. But here I would have gotten lucky if I had left off that absolute value on accident, because e and 1 are positive numbers. So absolute value doesn't change anything. 6, what's natural log of e? Well, natural log of absolute value. Absolute value of e is e because e is a non-negative number. What's natural log of e? It's 1. Minus, again, 1 is a non-negative number. So natural log of absolute value of 1 is equal to absolute value of 1, which is natural log of 1 gives you 0. 6 times 1 minus 0, 6 times 1, 6. So again, think of it just, I hope you appreciate the fact that this is a function. 6/t. Here, I'll just bring it up. 6/t is the reciprocal function scaled by a factor of 6. So the reciprocal function is 1/x. Looks like that. It's scaled by a factor of 6, which just means that you're stretching it vertically by a factor of 6. So looks like that. Now we're concerned about the region between 1 and e. E being the base of the natural logarithm, 2.718 and change. Which, again, so you're talking about the area of this region here. Here, I'll shade it. Y is less than equal to, and then we need to make sure it's above the x-axis, because that's always a given with with the definite integral. It's between the x-axis and the curve. So greater than 0. Technically greater than or equal to. So we're talking about a region that it's no special shape, that starts at 1 and stops at e, 2.71. It's a transcendental number. It's an irrational number. And it has this weird shape. The area is 6. To me, that's crazy. It's crazy. I hope you appreciate that. And even if you're not crazy about math and you're just doing this because you have to, I hope you appreciate how interesting that is. That we have this weird shape that is part of the reciprocal function between the x-axis, between 1 and e, and the area is 6. To me, that's just mind-blowing. I mean, not mind-blowing, close to mind-blowing. But it's super interesting, that's for sure. And I hope you find it interesting as well. Okay, let's stop this video for now. Let's make this a nice, quick, short, concise video, and we'll tackle the next 3 examples in the next video. I'll see you then.